This is George Lesniak with Autel. Thank you for joining us for this webinar, Introduction to ADAS Calibrations. Since this is a pre-recorded webinar, you won't be able to interact with me directly. However, you can still submit questions and we can get back to you through email. This webinar is intended for shop owners and technicians who are right now looking at getting into ADAS calibrations, and we're attempting to share some honest, factual information to cut through all the misinformation that you tend to find on the internet. This webinar is also helpful for shops who are just getting into ADAS calibrations to provide some of the best practices necessary to perform accurate ADAS calibrations. So let's go ahead and get started. As we begin, what is ADAS? So in its most basic definition, advanced driver assist systems can be a single function or a group of functions in the vehicle designed to help the driver pilot the vehicle, to make driving safer, to reduce the number of and the severity of accidents, but also to make driving more comfortable, especially on long trips. So there's a variety of ADAS systems that you can find on vehicles today. In fact, ADAS systems today can surround the entire vehicle. There's a variety of different assist systems from different manufacturers, and every manufacturer tends to have their own name for each of the systems, which tends to make it a little bit confusing for technicians as we're looking for service information. But as you look at this slide, all the different ADAS systems that are on vehicles today, if you think about it like this, they're really nothing more than software. The automotive engineers write software to create these different assist systems, whether it's adaptive cruise control or surround view monitoring, rear collision warning, blind spot detection, what have you. However, all of these systems, or let's say software programs, are dependent on one or more inputs in order to make those functions possible. So the inputs I'm talking about could be cameras, they could be radar sensors, and there's a variety of different styles of radar sensor depending on the exact need of the system being designed for the vehicle. There's ultrasonic sensors, there's LiDAR and other laser-based systems, thermal systems, infrared cameras. Again, there's different inputs for all the different systems, but something to keep in mind is on vehicles today, these individual inputs don't always work by themselves. You take something as simple as lane departure warning. That's generally a function of a forward-facing camera that would typically be mounted behind the windshield. That camera detects the lane lines and warns the driver if they're getting too close to a line on the left or right of the vehicle. However, more advanced systems like lane centering assist. Here's a system that is based on a forward-facing camera that maintains a vehicle in the center of its lane. However, it's not just the camera that makes that system function. It also uses a long-range radar. The camera and the long-range radar work together to detect objects on the road, whether they're within a few meters of the vehicle or maybe 100 meters in front of the vehicle. This fusion of sensors working together, it's actually called sensor fusion, allows the vehicle engineers to develop more and more advanced ADAS systems by allowing multiple components or existing components to perform other functions. To give you an example, things like brake assist, automatic emergency braking, adaptive cruise control, forward collision avoidance, those are generally all radar-based systems. However, on almost every vehicle on the road today, all of those systems also utilize a forward-facing camera. So for that forward collision warning to work, both the radar and the camera working together must be aimed together at the same point at a specific distance down the road. And again, that could be 100 meters or more. I want you to keep that in mind as we move forward in this presentation and start to discuss calibrations and when are calibrations necessary. You have to take into account sensor fusion because it's not always going to be as simple as just performing a single calibration after a certain repair. But before we get too ahead of ourselves, let's start taking a look at what is necessary for a shop as far as equipment and bay space, things like that. What is necessary for a shop to have in order to start or get into the ADAS calibration business? So it starts with a diagnostic tablet, a scan tool. A scan tool must be capable of initiating calibrations on the wide variety of vehicles that you intend to service. So you know your business, you know the vehicles that your customers own, that you're servicing on a regular basis. You need to ensure that whichever ADAS scan tool you purchase, it meets your needs for today and moving into the future. One very important note, the scan tool does not perform the ADAS calibration. The scan tool merely initiates the calibration. The scan tool performs what is known as a function call. Connect the scan tool to the vehicle, you connect to, let's say, a forward-facing camera module, and you hit calibrate. The scan tool sends a request to that module and asks it to enter calibration mode. So the scan tool can either do it or it can't do it. It's not possible for the scan tool to do it incorrectly. It can only ask the module to enter calibration mode, and it works or it doesn't. So besides a scan tool, you also need what's called a calibration frame. The calibration frame is the foundation for your ADAS calibrations. This is what you are going to attach your calibration targets and different radar calibration accessories to. You need a calibration frame that is stable and has the ability to hold the variety of targets and calibration accessories for the vehicles and systems you wish to calibrate. Now, this happens to be our Autel standard calibration frame that we show pictured. However, some calibration frames aren't as substantial as what you see here. You look at the Honda factory system. It's made of 1.5 PVC pipe. Toyota's OEM system is a approximately 8-inch by 8-inch block of wood with a stick of wood attached to it, upon which you tape a target to perform camera calibrations. Hyundai Kia uses a camera tripod. I'm not poking at any of those. I'm just saying a calibration frame is what you hang your targets on. This particular calibration frame, the Autel, is intended to be used with a wide variety of targets and accessories. That's why it is so much more substantial than many of the OEM systems, because it has to have the capability of performing a multitude of calibrations on a variety of vehicle makes. Next, now you need all the different targets, patterns, and accessories for the different types of calibrations you're going to perform. Now, it really depends on your business model, how you want to run that, what type of calibrations you're going to be doing. But this is a question that you need to ask yourself. What kind of calibrations will you be performing? And then that will help you determine what kind of calibration accessories you may need to acquire. Then finally, you'll need information. The calibration procedures and specifications for setting up the targets, patterns, or radar accessories. It's those precise measurements that the OEM gives you from a specific point on the vehicle to a specific point in your targets, so the vehicle knows that the target is placed in exactly the right position. The real nice thing about the Autel system is all of this is included in a single component. Our diagnostic scan tool, the ADAS tablet, is a full function diagnostic scan tool. Works on a variety of vehicle makes, domestic, European, Asian, but it also has the capability of initiating ADAS calibrations. But it goes beyond that. It also has the illustrated step-by-step instructions to guide you through setting up your calibration frame, targets, and accessories to help you ensure that you're performing an accurate calibration. So this is the basic equipment needed for ADAS calibrations. Then you need to ask yourself, what types of systems do you intend to calibrate? This really depends on, again, your business model. Are you a glass installer and you want to focus on calibrating forward-facing cameras that are mounted to the windshield? Well, then you may focus your attention on lane departure warning type targets and patterns. Maybe you're a collision shop and you're going to be dealing with a lot of fender benders and minor, bumper impacts that would require radar calibrations. Radar calibrations is where things get maybe a little complicated, a little bit more involved, because there are so many different components or methods for calibrating a radar. And these are all dependent on the OEM. To give you an example, some OEMs, Toyota, Honda, Hyundai, Kia, some Subarus, among others, use what's called a corner reflector. It's a triangular device that's set at a specific distance from the vehicle. The radar sends out a signal that's gathered by this reflector and sent back to the vehicle, and that's how a calibration is performed. Well, that's fine if you're only working on Toyotas, Hondas, Hyundai, Kias, and some Subarus. But what happens if you're working on Volkswagen Audis and Mercedes and BMWs and other Nissan vehicles and Mitsubishis? And I think you get the idea. Every OEM designs their own methods for ADAS calibrations. So when you're looking at an ADAS calibration system, make sure that it has all of the different radar accessories that you need for the vehicles that you're going to be servicing. Whether it's a calibration plate for Nissans and Infinitis, or a reflector mirror for Volkswagen, Audi, Porsche, and some other Nissans, make sure your system covers the vehicles that you need. Then, do you want to perform your calibrations only stationary in your bay? Or do you also need a system that, besides being stationary, has some level of portability? A portable ADAS system gives you the ability to travel to other locations, other shops. Maybe you're a mobile tech getting into ADAS calibrations, or you're starting a new ADAS calibration business and you're going to be visiting other shops in your area, maybe collision shops, and performing calibrations for them. That's part of the questions, again, that you need to ask to determine which type of system is right for you. Stationary, portable, they both end up performing the same types of calibrations for the most part. It's just a matter of how do you intend to use the actual calibration frame. Then, are you interested in integrating ADAS calibrations into your alignment process? Our standard calibration frame, the stationary frame, has the ability of integrating into a variety of alignment systems, from Hunter and Ravaggioli, CHEM, Rotary, Atlas, Atlas Pro. All of these systems, the alignment system manufacturer sells a kit to allow those aligners to integrate the Autel ADAS system, so you can perform a wheel alignment and an ADAS calibration on an alignment rack in one seamless process. So if integration with an alignment system is important to you, you'd be looking at our stationary calibration frame, since our portable system is not currently able to integrate with an alignment machine. Then you have to consider bay space in your shop. Now, the bay space requirements for an ADAS calibration are determined by the OE. They set the space requirements, they set the target height and the target distance. But generally speaking, you can perform most ADAS calibrations in a standard 16 by 30 foot service bay. However, the OEMs require that these service bays are flat and level. And that's really an important feature for accurate calibrations. However, most service bays and repair shops were specifically designed not to be flat and level, to allow water to drain. Well, you have to take that into account as you get into your new calibration business, or you start to offer calibration service in your existing business. A flat and level bay is really important to accurate calibrations. A question I often receive is, how flat and how level does a bay need to be? Most OEMs don't give a specification. Some do, most don't. They just say flat and level. So if your bays aren't flat and level, I know some shops will re-pour concrete in a specific bay to make it flat and level. However, other shops may perform their ADAS calibrations on their alignment rack. Whether or not it's integrated with the alignment system, you can park the vehicle on the alignment rack, which is flat and level. And then if your calibration system has the ability to compensate for the height of the lift, you can easily perform calibrations right on your alignment rack. Our standard calibration frame does have a built-in calculator where you input the height of the alignment lift, and it will compensate by increasing the target height to ensure the calibration target and the vehicle are on exactly the same plane, ensuring an accurate calibration. Then there comes some calibrations like around view monitoring. Some vehicle manufacturers, Ford, some Volkswagen Audi, and some Porsche vehicles have very large around view monitoring patterns. So you can see this Lincoln SUV being calibrated here. Those around view monitoring mats are 5.5 feet wide and 37 feet long, and there's 2 of them. So besides that length and width, you also need room to be able to walk around the vehicle. So the bay space requirement for this particular calibration is in the 25 by 40 foot range. Now, most calibrations, especially camera calibrations, need to be performed indoors in a controlled environment. However, Ford specifically states that it is possible to perform this particular calibration outdoors, as long as the ground is relatively flat and level, and you're not calibrating in direct sunlight that would wash out the black in the target, where the camera couldn't recognize the contrast between the black and white. There's always ways around these bay space requirements if you get creative. Let's take a look at some best practices to ensure you're performing accurate ADAS calibrations. Starts with the calibration technician and what is the skill set required. So it starts with the calibration technician must be able to read, understand, follow, and many times interpret detailed instructions without skipping steps. Now, this is critical. This is not like changing a water pump or a timing belt or even performing a wheel alignment. Step-by-step instructions are critical to achieving accurate ADAS calibrations. Really is important not to skip steps. Now, I mentioned interpreting what the process or what the detailed instructions say. I'll give you some examples of that in just a couple of slides. But sometimes the way an OEM writes a procedure, what they say isn't necessarily always what they mean. And you'll see what I mean in just a second. So you need to be able to make precision measurements with a metric tape measure. This is one thing that kind of scares a lot of technicians. I know we're not real big on the metric system here in the United States. However, every OEM provides their ADAS calibration measurements in metric, either in millimeters or centimeters. I know that you could get on your smartphone and you can do a conversion and convert centimeters to inches. However, that just brings in a possibility for error. And I see it happen all the time. So one of the reasons we actually supply 2 metric tape measures with our calibration system is to make this simple and straightforward. Some vehicle manufacturers still instruct us to use a string line and a plumb bob to help determine vehicle center line for placing the calibration targets accurately. Depending on the type of calibration you're performing, a blind spot radar calibration, you may need to create a true 90-degree right triangle on the ground. And you may have to actually draw that out on the ground and mark specific points with chalk or using painter's tape and a marker or a grease pencil. Drawing on the ground with chalk, that also important skill level that we learned in preschool, is now a valuable skill as we get into ADAS calibrations. These markings you make on the ground, as you see in the illustration, you may have point A and point I, point Z, the distance between 2 measurements. You're going to need to be able to read these marks as you go through the step-by-step instructions of setting up for a calibration. You'll need to be able to use a level, whether this is a spirit level, a bubble level, or a laser level, sometimes both. And you'll need to be able to make precise adjustments to your calibration system to ensure that targets or accessories are placed in exactly the right position. Next, documentation. This really isn't something that's optional, although a lot of shops do skip it. Documentation is probably the most important step to protect you and your shop for liability issues from lawsuits. Documentation will prove that you did everything that you were supposed to do when you performed the calibration. It won't be left up to your word against theirs. You'll have the pre-scan report that shows exactly any faults that were on the vehicle when the vehicle came in. It's really important to perform a pre-scan report before you start working on the car, because the indication is this is how the vehicle was delivered to you. I know in the real world that's not always possible. You may get a vehicle from a collision shop that has to be repaired before it can be calibrated, but still, the pre-scan is how the vehicle was delivered to you, even if repairs were made before that. As you're doing a pre-scan, you can also do a quick walk around the vehicle and do a visual inspection and photograph any pre-existing damage, scratches, dents, dings that may be in the area where you're going to be working, performing a calibration. And if your scan tool and your ADAS calibration system allow it, you could actually attach those photos to your pre-scan report. So when you save that, all the photos and the documentation are all together. That's actually the way the Autel pre and post-scan report works. You can attach photos to the pre-scan and to the post-scan to document, again, pre-existing conditions or other things like your calibration setup. Then when you're performing a calibration at the very end, you'll get a screen on your scan tool that says calibration completed successfully. You want to do a screen capture of that and add that screen capture to your post-scan report. Sometimes you may forget to do that screen capture. That's okay. You could go back into the module that you calibrated and look at live data PIDs and find the PID for calibration status. And if it says calibration completed or calibration success, you could do a screen capture of that and add it to your post-scan report. And then the post-scan report. This is after you've calibrated and test driven the vehicle. You got all that documented. Bring the vehicle back after you're satisfied that the system that you calibrated is functioning properly. Then do a post-scan report that will show the state the vehicle was in when you're delivering it back to either your customer, a consumer, or to the other shop that you're contracting with. Photographs. These are photographs that you could add to a report or save with your printed documents, an overall photograph of the vehicle. Some insurance companies want a photo of the license plate. having a photo of your calibration setup could be important to show that you're using a professional system. And then it's always nice after you're completed and you're delivering the vehicle, have the customer sign the bottom of a printed report. Maybe give them a copy, but definitely keep a copy for yourself and plan on an organizational system that will allow you to maintain those records for multiple years, just in case something happens. Next is your calibration environment. This is your base space. This is inside your shop. ADAS calibrations, as we mentioned before, require a flat and level floor, bright, even, controlled lighting. This is part of what I was talking about earlier, about interpreting what the OEMs say. Bright, even, controlled lighting means you're performing these calibrations indoors, because you really cannot control outdoor lighting. So controlled lighting means you don't have stray lighting from windows or lights on the wall shining from the sides or behind the targets that could confuse a camera or potentially cause a calibration failure, or even worse, a miscalibration, an inaccurate calibration that maybe was still successful. That's a real important thing to cover. A successful calibration does not mean the calibration was accurate. The only way to ensure an accurate calibration is to follow all of the step-by-step instructions to the letter without skipping anything. Because all of these instructions that you're provided are assumed by the camera that you followed those instructions. So when you're placing a target, the camera assumes that you did everything right, and the only thing it's going to be seeing in front of the vehicle is the target. If you've got clutter in the background, something like that, and the camera happens to see what appears to it to be maybe a checkerboard pattern, it could actually calibrate on a different object, different than your target, and calibrate successfully. But when you test drive the vehicle, the system may not function properly. It wasn't accurate. And then for radar calibrations, the OEM will tell you how much free and clear space is necessary to perform that calibration. An area in which there are no objects of metallic mass that would confuse a radar sensor and cause radar reflections back to the radar sensor, causing a failed calibration or, again, an inaccurate calibration. Here's an example of a less than ideal calibration environment. This particular technician was having a problem with this Toyota Camry. He's performing a forward-facing camera calibration, and on this vehicle, it's called a sequential calibration. That small target in front of the vehicle is actually moved to 3 different positions: center, vehicle left, and vehicle right at specific distances apart. So the camera actually calibrates in 3 steps: center, left, and right. When this technician was calibrating, every time they moved the target to the vehicle right, the calibration failed. It always passed center and left, but failed right every time. They couldn't figure out what was going on. And right there in the documentation on how to perform this calibration, it specifically states, make sure there's no clutter or windows in the background. See the windows on the bay door? Those needed to be covered with cardboard and then the calibration completed. However, when they showed me this photograph, I see some other issues that are concerning to me. The different signs on the door or even on the wall, the exit sign, everything that's in the background is laid out as squares and rectangles. There's a possibility that the camera is seeing something in the background and attempting to calibrate on it, and we won't know that until we take the vehicle out and drive it, and maybe a light comes on the dash saying lane departure warning is disabled, or the system doesn't act the way it's supposed to. The solution here is actually quite simple, especially if you follow the Toyota OEM instructions. They simply say put a piece of cardboard behind the target to block out the clutter in the background. Some shops will hang a curtain or a painter's tarp. It doesn't need to be fancy as long as it's a plain color, white, black, gray, tan, something without a pattern to it that will cover up all that clutter in the background, will help you perform more accurate calibrations. So now here's what it really comes down to: the vehicle preconditioning instructions. These are different for each vehicle make. They're different for each form of calibration, but there are some commonalities between, and I've got some examples here on the screen. So these preconditioning instructions are what the OEM states are necessary for us to check or do in order to perform an accurate calibration. So for instance, all fluids to recommended levels. Sometimes they will specifically call out the engine oil and the coolant. Make sure the gas tank is full. This is probably the most often skipped step. And it's a critical step because of what the OEM is trying to do here and putting this vehicle in a specific stance to make a calibration successful. Adjusting tire pressure to placard value. This means adjusting it to placard value, not to the air pressure that the customer likes to run in their tires or the air pressure that you think is best. Again, adjusting to placard value ensures whatever module we're calibrating that the vehicle is sitting properly. We're trying to duplicate the way the vehicle was sitting at the end of the assembly line when it was calibrated before being delivered to the new vehicle dealer for sale. It's important that the windshield is clean, especially in front of the camera, that the dashboard is clear, that there's no objects on the dashboard that might reflect in the windshield and again, confuse the camera. No load in the vehicle. There can't be any, salesman's briefcases in the back seat or, cases of flyers, car seats. The trunk can't be full. If you're dealing with a van or an SUV, there can't be a bunch of contractor equipment in the back. It's all about proper weight distribution and having that vehicle set in a proper stance. So all of that load would need to be removed from the vehicle in order to perform an accurate calibration. So many of these things, like for instance, you got a vehicle coming into your shop, you're going to be performing a calibration, you just let the consumer know. Make sure the gas tank is full and there's no extra load in the vehicle before you bring the car in. That way you won't have to worry about it. Same thing with a contractor. These aren't optional steps. These are all absolutely critical to the accuracy of ADAS calibrations. Ensure all the lights are off and the doors are closed. You want the lights off for a couple of reasons. One, you don't want to drain the battery. Two, you don't want headlights or driving lights shining on your calibration target that, again, may wash out some of the blacks and the vehicle camera may not be able to properly identify the contrast between black and white. Ensuring all the doors are closed. An open door during a calibration would cause some leverage as the weight of the door slightly tilts the vehicle to one side or the other, and that can throw calibration off. It's a very good idea. Strongly urge you to connect a vehicle power supply, a battery power supply to maintain battery voltage during a calibration. Many times the OEM will say, ensure the front wheels are steering straight ahead. This doesn't mean turn the steering wheel until it looks like the wheels are steering straight ahead. Here is the example of interpretation, because here's what this sentence means. The OEM is looking for the front wheels to be pointing straight ahead while the steering wheel is centered and the steering angle sensor is at 0 degrees. Some OEMs will go as far as to say, if you can't perform all three of those, that the vehicle needs to be aligned. So what they're getting at is, again, the wheel straight ahead, steering wheel centered, and the steering angle sensor at 0, because the steering angle sensor is a critical input to both forward-facing camera and forward-facing radar. The rear wheels steering straight ahead. This has nothing to do with rear wheel steering. This has everything to do with rear axle alignment, performing a wheel alignment and adjusting the thrust angle until it reads as close to 0.0 degrees as humanly possible. Some vehicle manufacturers give you a range. Many Toyotas will say within 0.2 degrees. Anything outside of that in an ADAS calibration can't be accurate. The reason is, as you know, thrust angle is the direction in which the vehicle is going to be driving down the road. Vehicle center line is the direction that the body of the vehicle is pointing. Most ADAS components, forward-facing cameras, forward-facing radars, are mounted or calibrated to the vehicle's center line. It's important that the thrust angle and the vehicle center line match. So where the car is driving is also where the vehicle is pointing, because that is where the sensors and cameras are looking. So let's put this into an example. So what the OEM is trying to do with these preconditioning instructions is determine that the camera position is exactly the same as when the vehicle was calibrated at the end of the assembly line. What they're looking for is camera height and the camera pitch, the angle that the camera is tilted down in its bracket so it can be aimed at a specific point, maybe 100 meters down the road. So this height and pitch are critical to an accurate calibration. So here we have a vehicle. We followed all of the preconditioned instructions to the letter. The gas tank is full, oil and coolant are full, tires are at placard value, there's no load in the vehicle, and our camera height and pitch match, and we perform a calibration. We can feel satisfied that that calibration is accurate. However, so here's that same vehicle being set up for a calibration. The camera is looking at a specific point, and that happens to be the center of our calibration target. The OEM tells us in this case that that target needs to be positioned 2 meters in front of the vehicle, measured from the center of the front wheel, and a target is placed at a specific height, which matches the camera height minus the pitch. So the camera will be aimed precisely at the target. However, in this example, we felt we didn't need to follow the preconditioning instructions step by step, so we chose not to fill up the gas tank. And this vehicle, which has an 18-gallon gas tank, came in and it's got an eighth of a tank of gas. We chose just to go ahead and calibrate, because what would it matter? So our vehicle, because we're missing about 65 pounds of weight in the back of the car, the rear suspension is the body's a little bit higher than it normally would be without that extra weight, which means our camera is going to be pitched down slightly. Now, we still have our target set at the proper distance and the target set at the proper height. However, now, because we didn't follow the instructions, our camera's pitched down, and again, as an example, an additional 1 degree. That 1 degree at 2 meters is 1.3 inches. Doesn't seem like a lot. What difference would that make, right? Well, the camera on this vehicle isn't designed to operate at 2 meters. It's designed to operate up to 100 meters. That 1 degree of deviation at 100 meters is 66 inches. The camera will be looking low 66 inches, because when we perform a calibration, we are teaching the camera what good is. So in this case, the camera was looking low. We calibrated it. It was successful. We taught the camera that looking low is good. Well, in this example, this vehicle uses the forward-facing camera for lane departure warning. We take the vehicle out, we test drive it. Lane departure warning works flawlessly because the camera is looking closer to the vehicle. However, this vehicle also utilizes the camera for adaptive cruise control, forward collision warning, and automatic emergency braking, along with the radar sensor. The issue that we face is when we calibrated this camera, and it's supposed to be able to see that vehicle at 100 meters, that our radar also detects at 100 meters, our camera is actually looking at the ground at 65 meters and never sees the car. This will cause a decrease in reaction time of critical systems like automatic emergency braking. Now, if you want to read details about this phenomena, IIHS, the Insurance Institute for Highway Safety, did a study of exactly this. They changed windshields in a bunch of vehicles and they documented the reaction time of automatic emergency braking based on very slight changes in camera position. They found that a change of as little as 0.6 degrees in camera position could cut the response time of automatic emergency braking in half. That's a difference between a vehicle stopping safely every time or a vehicle getting into a collision every time. So very, very critical. You have to think about how the systems work, not just what you think they do. Changing a windshield and calibrating a camera doesn't mean that camera's only being utilized for lane departure warning. We have to think about all the systems and sensor fusion and how everything is integrated. Now, the same issue could also come into play with yaw, or the side-to-side movement of a camera. If we don't properly position a camera in its bracket, or a windshield on the vehicle, or a radar sensor in its bracket, changing the physical positioning of the camera side to side 1 degree, again, is 66 inches at 100 meters. It's the difference between a camera looking in its own lane or looking in the lane next to you. This is actually a repeatable phenomena, something that's been in the news recently, of vehicles that are engaging automatic emergency braking when there is no potential for a collision, because either the camera or the radar are looking in the wrong lane. And when they see a vehicle in that lane, they assume it's in the lane in front of our vehicle because we calibrated the camera. The camera trusted us that we were going to follow those preconditioning instructions. So it believed that the calibration setup was accurate. So it's really, really critical not to skip any steps. So when is calibration necessary? This is by no means a complete list, but camera calibrations, obviously you repair or replace a windshield, the camera needs to be recalibrated. If you simply remove a camera from its bracket and just snap it right back in place, according to the OEMs, that camera needs to be recalibrated, because you cannot guarantee that it was placed back in exactly the same position that it was in when you removed it. A wheel alignment, we already discussed. Any change in thrust angle means the forward-facing camera and maybe, more than likely, the forward-facing radar would both need to be calibrated. Now here's something. A question comes up. A vehicle is properly calibrated. It's never been in a collision. It's never had a windshield changed. Maybe it hit a pothole and now it needs an alignment. Vehicle comes in to a shop, the alignment is performed, and the thrust angle is adjusted back to the factory setting of 0.0 degrees. Since the camera was calibrated before the pothole, why would I have to recalibrate it after I aligned it? Here's the answer. Every camera, every radar sensor has the ability to some level to learn, to adapt to changes in vehicle conditions. So when we're performing a calibration, we're performing what's called a 0-point calibration. We're teaching the radar or the camera what its 0 point is to give it the ability to adapt to changes in load, to changes in ride height, changes in tire pressure, changes in the amount of fuel in the tank. The only way that it can be accurate is if we properly perform that 0-point calibration. So in this particular vehicle that hit a pothole, knocked it out of alignment, where the vehicle is driving is no longer where the vehicle is pointing. Over time, the camera begins to learn this and it adapts to it. We perform the alignment, we correct the alignment issue. Now the camera has compensated and will be overcompensated in the opposite direction if we don't calibrate it. Now, will it eventually learn? Maybe. However, if you don't properly calibrate a vehicle after an alignment, you or your shop could be held liable. You're the professional. You're the one who needs to know what services would be would maybe in tire size or ride height. Anything that changes the ride height of a vehicle from its factory spec may require one or more calibrations. Now, on the radar side, much of this is very similar, minor collisions. A bumper, minor fender bender, or just a bumper touch in a parking lot that requires a little bit of resurfacing and repainting would still require recalibration. If you're going to do any refinishing to a bumper, you're changing the type of paint or the thickness of paint. We need to teach that radar sensor about those changes. Bumper covers removed. What about vehicles that require the bumper cover to be removed when you're changing an air conditioning condenser or a radiator, or some vehicles when you're doing an AC compressor, or any number of repairs on the front end of a vehicle? If the vehicle is equipped with a radar and you take that bumper cover off, service the vehicle and replace it, that radar needs to be calibrated. Many newer vehicles, when I say newer, 2016 and newer, actually have a radar sensor mounted to the grille. If a grille is removed and then replaced, that radar sensor needs to be calibrated. So calibrations, there's two types of calibrations. First, dynamic. Dynamic calibrations are initiated by a scan tool, and then the vehicle is driven under very specific driving conditions dictated by the OEM. So you may see conditions like in good weather conditions during the day with clearly visible lane markings, with objects on the side of the road like guardrails or garbage cans or mailboxes or pedestrians. Some vehicle manufacturers will say that they want other vehicles on the road, flat level road relatively, minimal curves, no changing lanes, no using turn signals. So each vehicle manufacturer will dictate the speed above 32, but below 67 miles an hour. You have to follow these precisely in order to get this dynamic calibration to complete. And then you will either get a status change on the scan tool or on the instrument cluster that when you start the calibration, the lane departure warning indicator may turn from green to yellow or orange, indicating that it's in calibration mode and it's not currently functioning. Once the calibration is completed, that indicator may turn to green, indicating to you that you have successfully completed that dynamic calibration. Dynamic calibrations aren't always as easy as they appear to be. If you live in an area or work in an area with a lot of traffic, a busy metropolitan area with bumper-to-bumper traffic on highways all the time, in a northern state where there's snow and ice on the road between November and March, performing dynamic calibrations can be very, very difficult. And one thing that you really can't do is repair the vehicle, give it back to the consumer and say, because it's raining out or snowing out, I can't perform this calibration. Bring it back when the weather clears and I'll calibrate it then. That opens you up to a world of hurt, of potential liability in the time between when that vehicle left and if it ever returns. Same thing holds true for you do the repair and tell the consumer to take the vehicle to a dealership. Once they leave, you are still responsible for that calibration, even though you didn't perform it. Not my opinion. It's the way the law looks at us performing calibrations in this industry. So beyond dynamic calibrations become static calibrations. Static calibrations are the one that we're doing in our service bay controlled environment, flat level floor, bright even lighting, all the things that we went over before, all the different targets, patterns, and accessories. And we perform that calibration in a very controlled, accurate environment. And then when we're done, we take the vehicle out and test drive it. There are some vehicle makes that actually have dual calibration. Honda specifically, some Hondas have a dual calibration. You perform a static, and then it immediately goes into a dynamic calibration that you have 30 minutes to perform. Subarus, Hyundai, Kias, some models will actually have the same thing, a static calibration followed by what they may call a test drive. But if you read the instructions, that test drive tells you how to drive the vehicle and the driving conditions that it's looking for. That is a dynamic calibration. That is a separate calibration from static. So when you're charging customers or dealing with another business that you're doing your calibrations for, or an insurance company, these are two calibrations with two totally separate setups. Same thing with a pre-scan and a post-scan. Those are separate events. And most insurance companies pay separately for those. So just ensure that you're charging appropriately for your hard work. So when we look at static versus dynamic calibrations, I know that there's been a lot of rumors that all calibrations are going to become dynamic or vehicles are going to become self-calibrating. Unfortunately, that is not true, at least according to the OEMs. Right now, vehicles between 2009 and 2020, 56% are statically calibrated. 37% are dynamic. There's 5% that are both static and dynamic. And there's a minority, 2%, that actually give you a choice between static or dynamic. Static always being the preferred method, and dynamic is either when you can't perform a static or you want to fine-tune the calibration afterwards. Question comes up, what are the OEMs doing with calibrations? Well, right now, the trend is, for some OEMs at least, to start steering away from dynamics towards static calibrations. Fiat Chrysler, for instance, Dodge and Ram trucks, Dodge cars, Chrysler vehicles. Generally, all the forward-facing camera calibrations have been dynamic. However, they're going to start introducing, with the 2020 model year, static calibrations as an option. It'll be an either or. And as they move forward, more and more models will have this either or until they finally choose the preferred calibration method of static. The reason they're doing this, one, accuracy, and two, that controlled environment. It's difficult in busy metropolitan areas, even for the dealerships, to perform dynamic calibrations, and they know that they cannot return a vehicle to a consumer when it is not properly calibrated. So you're going to start seeing this shift over to static calibrations from all vehicle manufacturers. And keep an eye out for some new legislation for ADAS and autonomous vehicles. And in that legislation, at least according to the current status of the legislation, static calibrations are going to be mandated in the future. And also keep in mind that starting in 2022, automatic emergency braking is going to be mandated on all new vehicles. So right now, there's over 61 million vehicles on the road in the United States that are equipped with ADAS, and it's increasing every single year. And the systems are becoming more and more complex, and sensor fusion is growing, which means a simple repair service could mean 2 or more calibrations would be necessary to be performed after that service or repair. So with that, it brings us to the end of this webinar, Introduction to ADAS Calibrations. If you do have any questions, please feel free to submit those, and we will be responding to you through email. And I hope to see you on one of our upcoming live ADAS calibration webinars coming soon. Thank you and have a great day.